So thank you, Mark, for your introduction. Hello, everybody. I would like to welcome you to today's presentation. As was said, the title is Antenna Analysis and Design with Characteristic Mode Analysis. And actually, before we get to the characteristic modes, I would like to point out some antenna design challenges, or especially integrated antenna design challenges. They are nicely illustrated on these devices I have here on the slide, so like a mobile phone or a smartwatch. However, they are pretty general, so this should also give you impression what can be achieved by characteristic modes. So typically these antennas need to be integrated into some device. So we have a limited space for our antenna. With that, there are some inherent physical limitations which affects our bandwidth. And if you put the antenna to a space which is smaller than a wavelength, or much smaller than a wavelength, you usually face a problem with a narrow bandwidth. And also, if we look at today's communication devices, we need to achieve high data throughput, and we also need to achieve it at each time. So independent on the movement of a mobile phone, independent of state of the propagation channel. And this is typically overcome by MIMO technology, so multiple input, multiple output technology, which requires several antennas to be integrated into the device. And as I said, communication devices such as mobile phones are quite portable devices. Therefore, these antennas need to be placed on a common ground plane, and they are quite close to each other. Therefore, we need to consider mutual coupling between these individual antenna elements. All these problems can be tackled with using model techniques, or more specifically, characteristic mode analysis. This presentation will consist of 3 parts. First, I will introduce you to characteristic mode analysis. I will use often the abbreviation CMA. And then there are examples, several of them, which will gradually guide you, or I will guide you through the examples to understand how CMA can be used for analysis and improvement of the antenna. Next, we will move to a discussion about coupling and excitation. So in the second example, we will have already 2 antennas placed on a common ground plane, and we will look into the coupling between both of them. The third example will introduce some techniques which are used commonly to enhance the bandwidth. And finally, we will have an example from our commercial customer, more specifically Sunway company. Throughout this presentation, I will use two different approaches to simulate a device or simulate a structure. One can be named as a driven, and the second one is the modal characteristic mode analysis. When we speak about driven simulation, this is what we understand as a full wave technique, so there is no approximation to Maxwell equations, and we have some kind of excitation, whether it's a port, it's a mode on a transmission line, or it's a plane wave. The important thing is that we have some kind of excitation. And within CST, we have several numerical techniques which are full wave, and we can use them to simulate the device. Here are the icons of the solvers which represent them. So this is these are probably techniques you are familiar with. Classically, you put an excitation and simulate a structure. On the other hand, we have CMA, which is again full wave technique, so there are all Maxwell equations considered, but it's a modal analysis. And modal means that you don't have any excitation, and mathematically you can consider it as an eigenvalue analysis. So the output are some eigenvalues and eigenvectors. One important note on CMA, it is designed for radiating structures. This is connected to the fact that it is integrated with integral equation or multi-layer solver, and therefore we consider infinite open space. Of course, we can consider a layered medium within a multi-layer solver or infinite ground plane, but in general we are speaking about radiation in an open space. If you for some reason would like to see a modes of a cavity, you should use different solver. You should not use CMA. You should use our eigenmode solver, which is very often used for filter design or some acceleration, particle acceleration devices. First example I have here is very simple to understand. I think you have seen as antenna designers such a patch antenna in the past. It is placed on a substrate and fed by a section of a coaxial line which can represent your connector. So this is a driven simulation. We excite it with a port and we calculate S11 response. And we see that there are actually two resonances in S11, and you probably know that this type of antenna is used to create circular polarization. You can check how well the polarization is radiated by changing the polarization view of the far field into circular direction. We also know that circular polarization is actually a combination of two modes which are 90 degrees out of phase. And this combination actually creates a rotation, which we can also see on a plot of a surface current over the patch. But before there was no tool to get the shape of these fundamental modes, which then create the performance of the antenna. Now we have CMA, so we can identify actually the distribution of the current for each of these modes. We can identify the resonant frequency of each one of them. And of course, you can calculate all the properties of the antenna you are used to, such as radiation pattern, maximum gain. You can check the polarization properties of each mode individually. You can check the side lobes and so on. So this brings me to the dialogue, how to actually activate characteristic mode analysis. And you need to use either integral equation or multi-layer solver and switch the source type to CMA. After you start the simulation, you will get several results I will comment. First of all, you will get an eigenvalue. And there is an important property of eigenvalue of characteristic modes, and this is that it is dependent on frequency. So basically you get a curve of the eigenvalue versus frequency. And to label which mode is mode 1 and which mode is mode 2, you need to somehow decide or put a criteria. And this criteria is actually available in the dialog of the solver. Here you specify how many modes you would like to calculate and what is the frequency for sorting. In other words, what is the frequency at which I will label this mode, which one is mode 1, which one is mode 2. And the mode which is closer to resonance at this frequency will be labeled with a smaller number. Of course, you can calculate, as I've shown, the surface current distribution of each mode at desired frequency. You can also calculate radiation or magnetic and electric field. So I said that the eigenvalue depends on the frequency, and it also has a special meaning, and the meaning is that it's a ratio of reactive to radiated power. And from this, if we have a zero reactive power, so there is no stored energy in the system, we have a resonance. Thus, if we have eigenvalue equal to 0, we have a resonant frequency. So we can find this resonant frequency of each mode by looking at the crossing point of the eigenvalue. Another important property which we can calculate from eigenvalue is a quality factor. And the quality factor actually is inversely proportional to the bandwidth of the system which it can achieve. And we can calculate it by looking at the slope, or in other words, at the rate of change of the eigenvalue. These two modes I display have more or less the same quality factor. If you would like to learn more about modal quality factors, you should check this article from Miloslav Čapek from 2012, which is mentioned below. And there is another important result, which is modal significance. Modal significance is often used because it's quite intuitive, and it tells you how significant each of the modes is at each frequency. So here we see that first mode is most significant at 2.4 GHz, while second mode is most significant at 2.5 GHz. And again, we can find the resonant frequency. The resonance is when modal significance equals to 1. So again, we can find from this graph the resonant frequencies. To summarize this introduction to characteristic modes, I would like to add that if you have an excitation, so actually the response of the antenna is a combination of all modes which can exist on the antenna. However, we are lucky that if we have a structure which is smaller or comparable to the wavelength, we have only few modes which are significant. So in our case of the patch antenna, we have only 2 modes which are sufficient to give you the response which you will give by a driven simulation. And another important property I will show later is that this excitation can suppress some of the modes. So if you don't want some mode to be excited, you can do it by proper excitation. Let's look at the first example of the usage of modal results. This example is only single antenna placed on a substrate, but there are 3 modes which exist on this antenna. How this antenna was designed. So imagine you have a specification of the band or of the communication protocols you would like to receive. And in this case, we've chosen GPS, these GSM bands and WLAN band. The easiest way how to get some antenna which fulfills these requirements is put these requirements into a synthesis tool which is called Antenna Magus. Antenna Magus is a database where you can look for an antenna which can fulfill the requirements and choose maybe the one which is planar or which is easiest to manufacture or which is the smallest. It depends on you. So we've chosen this antenna displayed here. Then you click, you specify the frequency, the bandwidth, the radiation properties, and click on Design. And finally, you click on Estimate Performance. So what you will get the dimensions of the antenna, and you will get estimation of the performance of this antenna. And final step is that you can export a parametric CST model, which we've done. And you can simulate it with one of the full wave solvers, again, driven simulation with an excitation. But as soon as you change something, in this case we changed the substrate, but you can also add a housing of your mobile phone or other device, and you can expect that there will be some change in the response. In our case, the change was that there at 2.4 gigahertz there is a bump above 10 gigahertz, and we would like to eliminate this rise of S11. So how to do that? So the question is, which parameter should I change in order to remove this error in the parameters, or this rise? And the question can be answered by characteristic modes. So in this graph, I performed a modal analysis by CMA. These are the dashed curves, and they displayed the modal significance of each of the modes depending on frequency. So we can see that we have three modes which have a resonance. To remind you, resonance is occurring when modal significance touches number 1. And I overlaid S11 in a linear scale to this graph. So we have a same frequency range, and we can, at each frequency, we can look at the S11 and we can look at the modal significance. At the 1.6 gigahertz, we see that the most significant mode is mode 1, but there are also other two modes which are less significant, mode 2 and mode 3. We can also check the current distribution of the excited or driven simulation, which is on the left, and mode 1 distribution, which is on the right. And you see that they correspond quite nicely to each other, but a careful look can also see that there is some part of a mode 2 and some part of mode 3 in the driven simulation. When we move to the second resonance, we see that the mode 2 is most significant, but there might be contributions of the other two modes, and the same at third resonance. This time third mode is the most significant, and there is a contribution of the two other modes. So now we would like to move, so actually to fulfill the requirements, which is the gray box. The idea is to shift this third resonance more closer to the second resonance, and therefore we will move this high peak at 2.4 gigahertz lower. And to do that, we need to find a way to tune mode 3 independently of the two other modes. And how to do that? We can look at the current distribution of each one of the modes, and if we find a spot where the current is low, this means that the mode will not be affected by some changes in this region. So, looking at the black circles, we see that mode 1 at the top layer will not be influenced by changes in this region. On the other hand, mode 2 and mode 3 will be affected. How large will be the effect? We need to do a parametric study, and these curves overlay all the modes with changed length of these strips. And you see mode 1 doesn't change at all. Mode 2 has some change in the resonant frequency, but mode 3 is affected the most because it changes both resonant frequency and the bandwidth. We can do the same analysis with the bottom part, which the suitable point for tuning is actually the length of the strip. So by this procedure, we have found a suitable candidate for tuning the antenna, suitable parameter candidate for tuning the antenna. And if we, based on this information, if we change the original structure and change these two lengths by 0.5 millimeters, we get the S11 green curve, which fulfills our requirements. So to summarize a little bit this section, so you have seen what are characteristic modes. You have also seen that actually the driven simulation or the real performance of the device can be understood as a combination of characteristic modes. And last, you have seen that this information can be suitable for tuning the antenna. So let's get to the next part. And in this part we will have two antennas placed on a common ground. The question here is that we should design an antenna for MIMO, multiple input, multiple output operation. We are given some space, so we have some space limitation, and we have to place two antennas in such a way that they will have an orthogonal radiation, so there will be low correlation between the radiation patterns. We will have low cross coupling, so low S21, and we will have sufficient bandwidth. In this case, we have chosen the bandwidth for LTE communication standard or several LTE bands, which are in the range of 2.5 to 2.7 gigahertz, roughly. At this frequency, the size of the mobile phone is roughly comparable to the wavelength. And I will show you two design approaches: standard design, which uses inverted F antenna, and design with characteristic modes. So first, the standard design has been done by designing a primary antenna, either driven or CMA-based design, doesn't matter, in the first step. In the second step, you independently design a second antenna to the frequency of interest. Again, it's a driven solution, characteristic modes haven't been used. And finally, you need to optimize the position of such an antenna in order to minimize the coupling. So you know that if you will be maybe closer with this antenna, with the second antenna to the first antenna, there will be higher coupling than if you orient it a different way. To do that, there is a 3D model which has been simulated with frequency domain solver, and we need to match the second antenna in order to have an optimal performance of this antenna. And this is done at a circuit level, displayed on the top. And we have a simple matching circuit consisting of inductor and capacitor. We optimize the values of these two elements. And this can be nicely done by using by controlling the flow of the operation of the simulation. What we can do, we can set up a nested optimization. So there is an outer loop displayed in a blue, and this outer loop of the optimization will move the antenna around the common ground plane. And we will be looking at the coupling between these two antennas. In the optimization which is inside this first optimization is a circuit simulation which is much faster than a 3D simulation to optimize the matching circuit. And in the end we evaluate the S parameters and we have the optimal result here. So you can see the red curve is actually the primary antenna. It is very nicely matched within the band of interest. The blue antenna is also matched to maybe minus 20 or 25 dB, but the bandwidth is not so good, and we don't have sufficiently low S11. The coupling between the two antennas, green curve, is quite low, minus 20 dB, because we have optimized the position of the antenna. So this was the standard design, let's say, standard design workflow. If we have characteristic modes, we can follow a slightly different procedure. We design the antenna the same way as we designed in the first case, and then we perform characteristic modes. The purpose is to find a mode which we can call a diversity mode. This mode should be decoupled from the first antenna, and therefore we can use it as a second antenna, in fact as a second antenna, which will provide the diversity for MIMO operation. And finally, we need to excite this mode, which we have found. And this last picture shows the way to excite it, which has been published by Robert Martens in 2013. So you can check the reference, which is displayed at the bottom side. So if we calculate the modes of this common ground, we see that there are 10 modes which have some significance in this frequency range. From these 10 modes, or maybe you can check just the most significant modes, you can identify the diversity mode, and you can also identify the mode coupled to the main antenna. I will tell you how you can identify which one is which one. And this is by looking at the current density which can go through the possible port of the main antenna. You can see that in case of a diversity mode, there is a low current flowing through this strip, which means that you will have low coupling to the port which is placed there. The main antenna, so when I place a port to the strip, I will excite this mode which is displayed on the left, because there is a very high current which flows through the strip. Then there is a question, how do I excite this diversity mode? So where to place the port? And again, very nice way to do that has been published by Robert Martens at the Loughborough conference in 2011. You can see the reference down at the bottom of the slide. And the idea is to put a slot to the ground plane at the place where the current is maximum, it is at maximum. This will not alternate the current density. So here is the picture how the mode will look like with the slot. But it will provide you a place where you can put a port to excite such mode. So we have done that. We have placed the slot to the maximum to the maximum current of the diversity mode. We have again attached the matching circuit, optimized the values of the matching circuit, and in the middle you can see the result. The solid line denotes the standard workflow with inverted F antenna, which I've shown you before, and the dashed lines denotes the characteristic mode approach. You can clearly see that the bandwidth of the approach when you use CMA is much wider, actually more than 3 times wider than the IFA case. But you can also see that the coupling is a little bit worse than in the case of inverted F antenna. So the coupling is shown by a green curve. It is still below minus 16 dB, so it will be probably okay. The antenna will work fine, there will be no problem. But let's see if we can improve this coupling. And we can do that by looking at the higher order modes, at the distribution of higher order currents. Here are plotted the most important currents, and you can see by looking at the intensity of the current inside the black circle that 4 of them will be coupled to the primary antenna, and then on the left we have the diversity mode I shown you before. And now the question is, we need to place the coupling element, the inductive coupling element, the slot I showed you, in such a way that we excite the diversity mode and simultaneously suppress the higher order modes. One of the ways or one of the positions where to place the coupling elements is again was again proposed by Robert Martens in the article below. And the positions, so actually there will be 2 coupling elements which will be excited out of phase. You can see the positions marked by blue arrows, and if you inspect each mode separately, you will see that this excitation will actually cancel 3 out of 4 higher order modes. So only 1 higher order mode will be excited by these 2 coupling elements. So let's try it. Let's put it to the model. We will need some feeding network here at the top, represented by ideal Wilkinson divider, and again matching network. We use the same logical process as in the cases before. Again, the standard design is displayed as a blue curve, and the CMA design is displayed as a dashed curve. So in this case we have we have slightly smaller bandwidth, so we have 13%, but still, if you compare in the gray region, if you compare the inverted F antenna and this CMA design, you can see that the performance is much better for the CMA. And more importantly, we designed the positions, or we selected the positions of the coupling elements in such a way that we suppress the higher order modes, which means that you will have very low S21 or very low coupling, much lower than minus 26 dB. So let's go to the next example, which will be quite similar to the one I showed you right now. Again, the task is the same. We should design antennas for MIMO operation. So we have a given space, we have to place 2 antennas, and so on. The difference is that we have a different frequency band. This time we will take a look at LTE 800 frequency band, which means that the size of the ground plane, or the size which we have available, is only 1/3 of the wavelength. And this brings a new challenges into the design, and you need to choose a little bit different strategy. So, at first, I would like to follow the same procedure as I showed you before. So I use antenna Magus to design the primary antenna. Then I use characteristic modes to find the diversity mode. In this case, looking at the curves, you see that there is one mode resonating near this frequency band LTE 800. Second mode, which is a green curve, resonates at 1.2 GHz, and there is no other mode resonating within the displayed range. However, we can still find our mode which is suitable for diversity, displayed as a last picture at this slide. So again, you have a lower current going through the port of the main antenna, and this mode is actually mode 3, which is displayed as a blue curve in the first plot. The problem or the difficulty is that this mode 3 is not resonating in the band which we are interested in, but is resonating much higher. It resonates around 2 GHz. Nonetheless, the mode exists, the mode is there, so we can place a coupling element and excite this mode as we did before. So this is a driven solution on the right. We design again the matching circuit. This time we need to match both antennas, so we need to put the matching circuit to the main antenna and also to the second antenna. And we get the frequency response. And what is interesting to note, that the main antenna performs very well. So in the whole band of interest, it has very low reflection coefficient. But this coupling element, or the antenna created by the coupling element, is very narrow band. So it's only 0.36 dB. You can see the orange curve, which has very narrow resonance. And the reason is that the second mode, which we would like to excite, it's actually resonating at 2 GHz, and by the matching circuit we are shifting it to the lower frequency than it's the natural frequency of operation. So therefore, to increase the bandwidth, we need to use a different strategy. And this idea actually comes from Zachary Myers and his article from 2013. You see again the reference down at the bottom side of the page. So you see that you have a first and second mode, and you need to shift the frequency of the third mode, which is our diversity mode. And if you look closely at the current at the ground plane, you can see that it's a current of a dipole. Dipole which is very fat and very short. So we know that we can change the resonant frequency of a dipole if we make it longer, but in this case we cannot make it longer, we have a limited space. Second option is to load the dipole by capacitance connected to the end of the dipole. In fact, this was proposed by Zachary Myers, and we applied it for our antenna, this idea, and actually added these strips which you can see in the picture to create a capacitance at the end of the ground plane. The effect is that we don't change mode 1 and the last mode, which are denoted by blue arrows. So if I go back, and you can see the curves here in the plot, and if I go forward, these curves do not change too much, but we have a new resonance which corresponds to the diversity mode, mode 3, and is denoted by green curve in the graph. You can also see here on the right hand side the current distribution created by this capacitive loading. So next thing what we like to do, we would like to shift the resonance frequency of this mode to be closer to the frequency band of interest. This can be done by parameterizing the length of the strip, and if you make this strip longer, you provide a longer current for the mode, and this will shift the frequency of this particular mode. So in the graph in the left side, you see how the mode changes if we change the length of this strip. Finally, we can put an excitation to an optimal length of this arm, and this time there is no need for any coupling elements, because we have available a strip with a high current intensity, and we can just put a port to the strip which has a high current. So we have mode 1, which is a red dot on top, exciting the primary antenna, and port 2, the red dot on the right arm. Finally, we need a matching circuit displayed below, and to optimize the values of this matching circuit. And you can see the final optimized design. The primary antenna is very wideband. It covers our LTE 800 band, which is marked by the green and gray column. It also will cover some of the bands for GSM, which are below 1 GHz. The diversity antenna, which is S22, marked by orange line, is optimized for downlink. So we will use this diversity antenna only for downlink. So the frequency band for downlink in this case is the lower band, denoted by a green column. Coupling between both of these antennas is very small, around -20 dB. The reason is that we excite orthogonal modes which are decoupled from each other. So finally, this brings me to the last example. This example has been provided to us from Sunway Communication AB. So I would like to take an opportunity to thank to Dr. Rohit Chandra and Dr. Charlotta Anderson from Sunway Communication AB, who provided us with the model. And I would like to also introduce you to Sunway. Sunway is actually a global company focusing on research and development and manufacturing of antennas, acoustic components, connectors, and related RF components. You can find more at their web page displayed on this slide. The antenna, this is a prototype of an antenna designed by Sunway, and it consists of a copper ground plane and metallic parts which are placed on a ABS structure, so structure made of plastic. The dimensions are displayed here, and if we take a look more inside the structure, we can see that again there is a primary antenna and there are two strips folded in a certain way which will be used for a diversity operation. And again we can use the same procedure to analyze this type of an antenna. We have two modes here between 0.7 and 0.8 gigahertz. The blue one is the most wideband mode, and it's actually the mode of the primary antenna. You can see the current flowing through the port. Then there is a red mode, mode 1, which has a very similar resonant frequency, and the current distribution is displayed here. This mode is decoupled from the first antenna because there is no current flowing or very small current flowing through the port of main antenna. There is also third mode which will not be used there because it is out of the band of interest, but what is interesting that this mode is also decoupled because in the port region you can find a current which flows in opposing direction. This current will cancel out and will basically not be coupled to the port. We need to, or it is necessary to design a network which will feed these antennas, and actually the main antenna needs a common mode excitation, or needs an excitation of port 5, and the diversity needs a differential mode excitation. There are also, you can also see ports 2 and 4 which are prepared for the higher band operation, but we will not show it here. We will use only the longer arms ports 1 and 3 for the diversity antenna. Again, matching network is necessary. And this is the performance of the prototype. So you can see that the main antenna has a very wide bandwidth of 31%. So it covers all the bands, all the LTE bands, which are below 1 gigahertz. You also have a red curve, which is a diversity antenna. It is not tuned for a particular band yet, but it has a potential of 4.3% bandwidth, which is sufficient both for LTE 700 and LTE 800 downlink. And we have a second resonance around 1 gigahertz for the diversity antenna, which is not used currently, but maybe used. The coupling is the lowest from all the examples I showed, so it's below minus 30 dB. It's almost reaching minus 40 40 dB. Because I spoke a lot about antennas for MIMO, I would like to also show you the MIMO performance parameters. And actually you can calculate within CST the common parameters for MIMO, like envelope correlation coefficient, diversity gain, multiplexing efficiency. You can take into account also mean effective gain. So in this graph, we see that the correlation for the MIMO antenna or MIMO prototype designed by Sunway is extremely low. It's below 2 or 0.0002. And you can also take into account efficiency or losses in the structure to calculate multiplexing efficiency. Again, very nice result for the antenna prototype. So I would like to summarize my talk or remind you what we have seen today. First, you've seen how to use the characteristic mode analysis to tune the antenna into its resonance or to find the parameters which can be used for tuning. Second, we have spoken about excitation, coupling and bandwidth, and for this particular example or for this particular topic, it was demonstrated on a mobile communication antennas. But the procedures which has been shown can be used in general in any type of structure. At this point, I also would like to comment on the complexity of the models I used here. So you see that they are relatively simple, or they are quite simple structures. This was meant for purpose to provide you with understanding on a simple structures. And also it reflects the fact that characteristic modes are used for creating a concept or creating a new design, so in the beginning of design process. Of course, you can simulate within CST very complex structures, and if you are interested in more details, you might want to check past webinars which are listed here. They are available through our webpage in the archive. You have to click on archive and watch the recording. So these 3 webinars, first one of them is the most recent one. It deals with interferences of the systems at the system level inside a communication device. Then there is a dedicated webinar for 5G antenna design. You also might want to watch a smartwatch webinar. This brings me to the conclusion. Characteristic mode analysis is fully integrated into CST Studio Suite, and you can use it if you have a license for integral equation or multilayer solver. If you don't have a license and you would like to try characteristic modes, please contact your local sales team, CST team. A characteristic mode analysis is often or must be used with other full wave solvers. So you have seen that throughout the presentation there was a switching between driven and CMA analysis. And finally you have seen what is CMA good for. So you can improve your antenna design, you can enhance the bandwidth, you can reduce the coupling between multiple antennas. So thank you for your attention. I'm giving back